Hello, my name is Jiwon Woo from Hankook Academy of Foreign Studies in Korea. Today, I will present my research about neutrino oscillations and particle accelerator experiments. In April last year, I read an article from Nature explaining about an accelerator experiment on neutrino oscillations and wondered how this neutrino experiment could explain the origin of the universe. From this experiment, people confirmed that neutrino and antineutrino oscillate differently and could explain matter-antimatter asymmetry in the universe. I was very interested in neutrino oscillations after I read the article and started my own research on neutrino oscillations. This slide explains what neutrinos are and how they oscillate. The neutrino is electrically neutral and interacts with other particles only through the gravitational force and the weak force. They exist in three different flavors called electron neutrino, muon neutrino, and tau neutrino. Neutrinos keep changing their flavor from one to another in a process called neutrino oscillation. This oscillation can be explained as a function of probability, and we call it the oscillation probability function. According to the standard model, in the early universe, the same number of matter and antimatter particles were created. Therefore, the same number of matter and antimatter particles should exist in the universe. However, in the current universe, matter is dominant, and the standard model is unable to explain this. To explain this, it was proposed that a difference between oscillations of neutrino and antineutrino could make a difference in the creation rate of matter and antimatter particles, and the accelerator experiments were planned to explain this. The graph in the bottom right is the neutrino oscillation probability function. The red plot represents equation number 1, and the blue plot is equation number 1 subtracted from 1. These two plots show neutrino oscillation. In this graph, the position with the first maximum oscillation rate is the neutrino detector's location. The detector's location can also be obtained from the value of L when equation number 2 equals 0. Delta M squared in equation number 2 is the energy difference between two different neutrino types when a neutrino oscillates from one type to the other. We can see which neutrino oscillates to which by calculating delta M squared. This is a brief comparison of T2K and U and LBNF. For these two experiments, I compared the position of the neutrino detector and calculated the delta M squared of the neutrino oscillations. First, the oscillation probability function was applied to the two experiments to calculate the detector position. Since the accelerator energy is low in case of T2K, it shows an oscillation function with a short period, whereas Dune LBNF has a relatively longer period. A short period means that the detector is close from the neutrino generator, and a longer period means that the detector is far away. In fact, it was confirmed that the position of the first maximum oscillation, calculated by differentiating the graph of each experiment, was similar to the actual detector positions. Second, as shown in the figure on the right, neutrinos have three mass states, which the neutrinos are distributed in. In general, it is known that muon neutrinos have a high probability of being in the highest mass state, whereas electron neutrinos have a high probability of being in the lowest mass state. Since the particle accelerator experiment is designed to generate muon neutrinos and detect electron neutrinos, approximately 10 to the power of negative 3 electron volts squared of delta M squared should be calculated. From my calculations, in both experiments, the delta M squared have a value in the order of 10 to the power of negative 3 electron volts squared, which proves that the oscillation from the muon neutrinos to the electron neutrinos was detected as planned in the particle accelerator experiment. Now on to the conclusions. The oscillation probability function was applied to calculate the position of the detector, which was then compared with the actual position. And by calculating the delta M squared of each accelerator experiment, and confirming that the value is about 10 to the power of negative 3 electron volts squared, it was confirmed that the neutrino oscillation from muon neutrinos to electron neutrinos was successfully carried out as planned. Thank you for listening.